Hello, everyone. Thanks for joining. This is the Applied ML Summit session on model governance and auditability. In this session, we'll explore the frameworks and tools that can help simplify the process to audit, track, monitor, and govern ML models, adapting to a dynamic environment. And we'll also highlight how you can apply model governance in practice. This is Rajesh Thalan. I'm a solutions architect at Google Cloud, focusing on machine learning. Let's get started. When you're building ML applications, it does not stop at deploying models. In fact, it's only the beginning. Let's take a quick look into the MLOps workflow to understand what it entails. After the business problem is framed, the workflow begins with experimentation phase, with data scientists iterating through various models, algorithms, and developing training pipelines. These pipelines enable data scientists to iterate quickly to create the optimal model. These pipelines should be treated as a software application and are version controlled and deployed to target environments through a CI/CD process. This pipeline is trained on production data to generate candidate models, which are then versioned and tracked, which are then tagged for release and picked up by a model deployment CI/CD job that goes through testing strategies such as A/B testing. Finally, model endpoints running in production are continuously monitored for the incoming data to identify any drift or the model inference themselves to detect the performance decay. This monitoring can alert teams early on when there is a performance degradation and act upon it. Let's take a peek into the monitoring part. There's a problem that occurs often for ML models. Machine learning models are trained on past data. Let's assume after you deploy the model, one of the data sources no longer gets updated. The machine learning model will just adjust to this, and its behavior will continue to be reasonably good and decay gradually thereafter. A real-world example that we observed at Google in the past. We deployed a pipeline that trained a new ML model every day. A bug got accidentally introduced in the serving stack, transforming a specific feature to a default value. Unlike other software systems, machine learning model is resilient to data changes and did not output any error. It generated prediction responses with lower accuracy scores. Since the serving data is fed back to the training loop to train the next version of the model, the problem persisted and got worse until it was discovered. There could be potentially more reasons why machine learning model may not work well after it goes live in production. The model is static, but the world around it changes. There might be a change in user behavior in the app due to any recent events, or there's a need for other signals to monitor the model's performance. You need monitoring processes that can track data distributions and manually inspect the data on occasion to reduce these kind of failures. Well, with what I say model monitoring, our goal is to make it easy to turn on monitoring for a model deployed on what is CI's prediction service. Almost as easy as just flipping a switch. Once the prediction endpoint is up and running, one can turn on a training serving skew detection or drift detection by running a single G-code command with no need for any extra setup tasks. Training serving skew measures how different is the data seen in production from what the model was trained on, and prediction drift measures how changes in prediction response in production over the time. There are two main measures that can be monitored and alerted on: feature distribution monitoring and feature attribution monitoring. Model monitoring compares the baseline and latest distributions observed from the prediction service using distance scoring algorithms. When the distance score exceeds the configured threshold, model monitoring identifies the skew or drift as anomaly. When an anomaly is detected, an alert is sent via email or cloud pops up via cloud logging. You can then visualize and analyze the feature value distributions from the UI and perform side-by-side analysis of these production data distribution and training data distribution to diagnose the issue. Based on the alerts, you can trigger retraining pipelines to address the performance degradation whenever applicable. In addition to monitoring feature distributions, model monitoring also supports monitoring feature attributions. Feature attribution explains a model's prediction on a given input by attributing it to features of the individual inputs. These are typically expressed as a feature importance scores. Under the hood, model monitoring uses explainable AI tooling with prominent algorithms such as SHAP, integrated gradients, and LIME to calculate these attributions. These attributions are monitored during serving to report any significant drift relative to training or baseline. Another useful tool in this realm is What-If tool, an open source tool developed at Google to visualize and probe into your models and to understand the data sets and the outputs of machine learning model with minimal code. The analysis from this tool can be helpful during training, model creation, and post-training evaluation. For example, using the tool, you can test performance in hypothetical situations or analyze the performance of different data features. You can also visualize the model behavior across multiple models and subsets of input data and for different machine learning fairness metrics. All right, now switching the gears. As your more models deploy to production, you may likely face more challenges managing these models and find an increasing need for model governance. During the experimentation phase, when prototyping and investigating modeling techniques is a huge challenge to keep track of metadata like metrics, parameters, and the version of code, data, and parameters used across the runs. And it's important for reproducibility of experiments. Organizations typically struggle to prove how a model was trained, and most cannot reliably produce a model from its dependencies. This becomes even more critical when operating in a regulated environment. There is a clear need for model governance, which helps minimize the risk to an organization when using the models. There are multiple stakeholders with varying interests and responsibilities in establishing a model governance process. For example, a data scientist who experiments with various models and deploys them has the responsibility to document model artifacts, the metrics, parameters, and the context around the training data and the model's potential use cases. Model governance is a framework, a set of processes defining how we manage models, manage access control policies, comply with audit and regulations, tracking model development and deployment processes. What you see here is an opinionated governance lifecycle, which is broken down by stages with governance principles, stakeholders, tools that enable necessary processes, and expected artifacts from each of the stage. We'll not go into this detail, but picking up that validation stage, which puts in checks for audit and review safety and performance metrics. This is of significant interest to internal audit boards who are responsible for reviewing and approving whether a model can be deployed to production or not. To enable this stage, there are tools such as Vertex ML Model Registry, ML Metadata, Model Card Toolkit that can produce artifacts to help the stakeholders to make the decision before the model gets deployed. Let's look into some of these tools. Vertex ML Model Registry is a central repository to manage the lifecycle of your machine learning models, irrespective of how and where the model was trained. You can import the models to the repository and organize, track, and view versions. You can also view the historical data and performance, and for retaining other metadata for audit or compliance purposes. Another important feature is the alias marker, which can help stakeholders understand at a glance which model is stable version and ready for deployment. This is useful when governing the model launch process. When a model version is ready to deploy, assign it to an endpoint directly from the Vertex ML Model Registry to deploy to a target environment. Vertex ML Metadata lets you record the metadata such as metrics, parameters, and reference to the code, data, and artifacts produced by ML systems. This metadata can then be queried to help analyze, debug, and audit performance of your machine learning system on the artifacts that it produces. Now, this actually enables you to compare across the experiments to find those effective parameters and different set of hyperparameters. You can track the lineage of machine learning artifacts for governance purposes, and also enable reproducibility to rerun retraining workflows. Model cards are another important artifacts to model governance. These are short documents that help organize essential facts of a machine learning model in a structured way, providing context and transparency into model's development and performance. Model Card Toolkit is an open source tool developed by Google, which simplifies and creation of model cards by automating just with a few lines of code, Python code that can be integrated into machine learning pipeline. It generates a shareable artifact that contains model metadata, metrics, and key graphs. The output is HTML or JSON files that can be saved as artifacts as the reference in machine learning metadata. The next in the arsenal is Vertex AI pipelines that brings together all these tools and processes that we discussed today. Pipelines help you to automate, monitor, and govern your machine learning system by orchestrating workflows in a serverless manner and enabling machine learning operation strategies. The core feature that enables governance is that pipelines automatically record and store workflow artifacts using Vertex ML metadata and enable the lineage of workflow artifacts. For example, a machine learning model's lineage may include the training data, hyperparameters, and code that was used to create the model. And data scientists can quickly convert their experiments into production-ready workflows by authoring them using the friendly Python SDKs based on TensorFlow Extended or Kubeflow pipelines. What we discussed today is only part of capabilities that enables you to monitor and manage machine learning models. Vertex AI is a unified platform to build, deploy, and manage model operations at scale. It has necessary core building blocks for data science, machine learning, and MLOps, making it flexible and, of course, secure. 3 key takeaways from what we shared today. First, machine learning lifecycle does not stop at deploying models. You must continuously monitor your models because once true does not mean forever. Vertex AI model monitoring can get you started. Secondly, data quality drives feature quality, which drives model quality. So analyze your data and probe your models with tools like What If Tool and understand that model behavior with changes in data. And finally, model versioning and provenance is key to reproducibility in the machine learning lifecycle. What if AI has necessary building blocks to manage models at scale with what if AI pipelines, ML metadata, and model registry, and a lot more. We have put together a few resources to learn more about the topic and get started. We hope you enjoy the talk. Thank you for listening.